In this video, we're going to be talking about turning points or relative maximums, relative minimums. The points or points at which a polynomial function switches directions. And what I mean by that is going up, then all of a sudden it starts going back down, or it's going down, then it starts going back up. This point and this point. Is a turning point. That's what we're talking about here. If the turning point is higher than any nearby point, as it is here, notice it's the highest point anywhere around. We call it a relative maximum. If the turning point is lower than any nearby point, as it is here, if I drew a box around this, this is the lowest point around. We call it a relative minimum. Maximum and minimum values are called extrema. Turning points define where the function is increasing or where it is decreasing, or whether it goes back to increasing. So at those turning points is the switch from an increasing function to a decreasing, or a decreasing back to an increasing. What we're going to do here says find the turning points of these functions. We're going to graph these functions on our graphing calculators. We're going to graph. We are going to then use, and this right here applies to the TI graphing calculators. We're going to use Desmos. You don't have to worry about these steps, but we're going to find out where is this function, where is its relative maximums, relative minimums, where is its extrema at. So let's go ahead and look at the graph. Okay, and here we see a picture of that graph. Notice the x to the third. I want to point that out from the last lesson. Notice since it is x to the third, we have an increasing, and then once it gets to this point, it starts decreasing, and then from this point on, it starts increasing again. This x to the third graph is an odd degree function. And notice to the right, it goes to positive infinity. To the left, it goes to negative infinity, just like we talked about the general shape of an x to the third last lesson. However, the relative maximums and minimums, the highest points, as this point right here is, and the lowest point around, which is this point. Okay. Now there are other points higher and other points lower, like this point here is much higher than this relative maximum, but it's the highest point around. So we have a relative maximum here, and all you have to do is click on the graph. It looks like at 0.7, 4.3. So let's come back over here, and our relative maximum, again, 0.7, 4.3. We have a relative minimum. Let's go back to our graph at right around in here, 3.3, negative 4.3, 3.3, negative 4.3. Now let's talk about where it increases and decreases, and we're talking about intervals here. So this is what the general shape of our function here, and our function increases. It's going uphill until it hits this. Now, when we're talking about increasing and decreasing, we're going to talk about intervals, x intervals. We're only worried about the x values. So my function, everywhere up to this point, it starts increasing, or it is increasing. So that'd be everywhere from negative infinity up to this x value, which was 0.7, which was right here. Then it starts going downhill. And it goes downhill until it gets to this point right here. And again, we're concerned only with the x values. So from here to here, which was at 0.7, because it started decreasing as soon as it left here, and it decreased until it got to this point, which was our other extrema, which was at 3.3, only the x values. Then what happens? At 3.3, it starts going uphill again, and it goes uphill forever. So from 3.3 to infinity, it increases again. And that's how you find your intervals where it's increasing or the intervals where it's decreasing. Okay, first problem. You see the function here says graph the polynomial function using a table. We're actually going to use Desmos. You could use a t-table, but we're going to use Desmos. We're going to plot the graph on here. Give us domain, range, and we're going to do all this stuff over here to the side. So take a look at this one on Desmos, and notice the general shape. We have a relative minimum, then it starts going uphill to this point, and that's your relative maximum. And let's go ahead and write those down on our sheet. So we have a relative minimum at 0, 0, and we have a relative maximum at 2, 4. Our domain and range, again, domain is what could x be? Is there any domain restrictions? Could I have any division by 0 here? Do I have a square root of a negative? And there's nowhere that this function is not defined. And then the more proof of that is this graph, as it travels to the left, continues traveling to the left forever. As it goes to the right, it continues traveling to the right forever. My domain is all values, all real numbers, from negative infinity to positive infinity. It's everything. Now, we will take and sketch out a graph of this thing just to remind you what it looks like. So we have 0, 0, 2, 1, 2, 3, 4, and we're just going to kind of sketch out a graph. So it comes down, goes up, hits this point, and then comes back down. So that's the general shape of our graph. Now, what about our range? What are our y values? And notice that my graph goes down forever, and there's no point as I draw these horizontal lines, there's no y values that I'm not going to hit. So therefore, my range is also all values from negative infinity up to positive infinity. My end behavior, as I go to the right on this function, my y value goes down. As I go to the left, my y value goes up. That would be a negative and positive infinity there. Where does it increase and where does it decrease? Now, here's where these points here come into play. We're only concerned with the x values. My x value here is 2. My x value here is 0. So my function, you always read this from left to right, goes downhill until it gets to here. So it goes downhill from negative infinity up until it hits 0. Now notice the interval negative infinity to 0, I'd put a parenthesis around 0. I don't include it. Why don't I include it? Well, think about what's about to happen. It starts increasing, and it increases from here over to here. It increases from 0 up to 2. Well, how can it increase and decrease both at 0? It can't. So we never include those ending points when we're talking about increasing and decreasing. Then at 2, what happens? It starts going downhill, and it goes downhill forever again from 2 to infinity. Our next problem. And we can give it a shot here. We can do us a t-table here. We can do a table of values. We plug in some x's, find some y's, pick some x values. I'd probably maybe -3, -2, -1, 0, 1, 2, 3. And let's see if we can get a general shape of this graph by plugging it in. Just keep in mind, again, always do exponents first and always multiply, like the multiplication by -4 will happen after that. When you plug these values in, here's what you get. And I just wanted to show you something. Here's where I'll plug these points in, and here's the graph I got. And I just want to use this to show you how valuable graphing software is, because once I actually look at the graph itself, here's what it looks like. You can't really tell unless you have more points what this graph is actually going to do. It's going to look something like that. However, where is this lowest point? Where is this highest point? However, when you're dealing with graphing software, look, you can tell low point, high point, low point, where those maximums and minimal values are located. And there you see where your local mins and local maxes are. Again, the local min is the lowest point around. That's the lowest point anywhere near there. So that's going to be at -1.8, 3.3. -1.8, 3.3. Then you have a local max there at the middle, and that local maximum is at 0.5. And then you'll have another local minimum over here, which is not the point that I had on the graph. It's actually at 1.1, 2.95, so about 3.0, 1.1, 3.0. 1.1 and 3.0. So you see here that you can have multiple local mins, local maxes. Now let's talk about domain and range. Now with a polynomial function, here's the thing. There's not going to be any discontinuity for our domain ever. So therefore your domain, you can always plug anything in there. It goes from negative infinity all the way to positive infinity. Now here though, you do have a range. Look, there's nothing down here. Your graph starts here. Now the question is, what is here? Well, we're talking about y values. So how low does this graph go? It looks like 1, 2, a little bit more than -3. Well, if you remember And that's supposed to be a negative 3.3 right there. If you remember correctly, this was one of our local mins. The lowest point on that graph, the lowest y value on that graph is right here. So therefore, my graph never goes anywhere below negative 3.3, and then it goes up forever. So therefore, the lowest y value, the lowest y that my graph has is right there at that local min, which was negative 3.3. Now let's talk about end behavior. As your graph goes to the right, look, it goes up. So that's therefore as we approach positive infinity, my graph goes up. As we approach negative infinity, as we go to the left, my graph also goes up. So there you go. Your increasing and decreasing intervals, again, we're only concerned about x values here. And let me go ahead and write down those x values that were on our minimum and maxes. Let's do a different color here. This was a negative 1.8 was the x value there. My x value here was 0, and my x value here was 1.1. So therefore, my graph from the left to right starts decreasing first, and we decrease everywhere from negative infinity up to this x value of negative 1.8. Then what happens? Then we start going uphill at negative 1.8, and we go uphill until we get here at this x value of 0. Then what happens? Then I start going back downhill, and we go downhill until we hit 1.1. So 0 up to 1.1, and then we start increasing again from 1.1 forever. Okay, the next one, number 3. Let's take a look at our graph. And here's a look at that graph. Notice that here's the highest point. It's kind of like the top of the mountain there. That's the highest point anywhere around. Then your graph starts going downhill until it gets to about right here. And that's going to be our lowest point around. So you got a local minimum there. Then it starts going uphill a little bit, and it hits this right here, which will be a local max. So you go from a low point here to a high point here, and then you start going back downhill, and you go downhill forever. And you can see what happens as we go to infinity. So what I've done, I went ahead and sketched that graph, and it's not a good looking sketch. I went ahead and labeled those local maximums and minimums. Our domain, again, anytime we're talking about polynomial functions, you can plug in anything you want to. However, there is going to be sometimes a high point or a low point. So my range, we go down forever, so we start at negative infinity. However, we only go up to this point. And that y value is going to be located at our local maximum there, which is right here. The highest that my graph goes is about 6.5. Since that is a point on your graph and it's filled in, that's the reason we put a closed bracket there. It's because that is a point on my graph. In behavior, as I travel to the right, notice that my graph goes down, so it goes to negative infinity. Well, what happens when I travel to the left? My graph also goes down to negative infinity. Intervals where I'm increasing and decreasing. Let's take and actually write these x values on our graph. My first local maximum had an x value of negative 1.6. That's my x value here. Then we go down to this local minimum right here, which was located at 0.4. Then we go uphill to here, which is located at 1.2. So there's all your x values. So let's talk about increasing intervals, and we always read these from left to right. My graph goes uphill to this x value, so everywhere from negative infinity up to negative 1.6, I'm uphill. Then I start going downhill at that point. And I go downhill from that x value, negative 1.6, up to this x value, which was 0.4. Then at this x value, over to this x value, I go uphill again. So from 0.4 up to 1.2, I'm uphill. Then I'm downhill from there to infinity. Okay, number 4, that's our last one. 2x to the third minus 4x squared minus x. Let's go ahead and take a look at our Desmos graph. And here it is. From the looks of the graph, looks like we have a high point here at negative 0.1, comma 0.1 if you round it. We're going uphill until we hit there. Then all of a sudden there we start going downhill on our graph till I hit this local minimum, which is about 1.5, negative 3.8. Then from there on, this is an uphill. Remember our x to the third graph, how it's uphill, downhill, and then back uphill again. If you remember those end behaviors for an x to the third. So let's go ahead and kind of sketch this graph out on our paper. Okay, there's kind of the general shape, and I went ahead and put those relative maximums. Now, the question is, to the bare eye, it would look like that maximum right there was at 0, 0, or maybe a little bit to the left. It's really hard. How would you ever figure out where that maximum is without Desmos? The question is that comes into play with calculus, and when you start dealing with calculus, we'll start talking about extrema again, and we'll show you the algebraic or calculus way of finding those maximums and minimums. However, here is my max and mins from Desmos. My domain, again, for these polynomial functions will be all real numbers. My range, my graph this time goes down forever and up forever because it is that general x to the third shape, and we know what it does to the left and to the right. So my range is also all real numbers. My end behavior, as I travel to the right on my graph, my function goes up. As I travel to the left, my function goes down to negative infinity. Now, where does it increase and decrease? Let's go ahead again and label these x values. This x value is negative 0.1. This x value is 1.4. And again, the reason I'm concerned with those x values is that's where my graph stops increasing and starts decreasing, or vice versa. So reading it from left to right, my graph goes uphill till it gets to that x value. So it's increasing from negative infinity up to negative 0.1. Then it has to start decreasing if that's one of our local maximums or mins. And it decreases until it gets to this point, which is 1.4. Then it starts going back uphill again. And at 1.4 on forever, it does increase.